Hello everyone, in today's topic we are going to talk about operation on sets. The universal set is a general set that contains all elements under discussion. John Venn created Venn diagrams to show the visual relationship among sets. Universal set is represented by a rectangle, and we can use a capital letter U to represent universal set. Subsets within the universal set are depicted by circles or sometimes ovals or other shapes. Representing two sets in a Venn diagram, we have disjoint sets, two sets that have no elements in common. So this is the Venn diagram representing disjoint sets. We also have equal sets. If A is equal to B, then A is a subset of B and B is a subset of A. So we have this Venn diagram to represent equal sets. Sets with some common elements. Some means at least one. So we have this Venn diagram to represent sets with some common elements. And we have also proper subsets. All elements of set A are elements of set B. So this is the Venn diagram that represents proper subsets. We go back to the complement of a set. The complement of set A, symbolized by A prime, is the set of all elements in the universal set that are not in A. This idea can be expressed in set builder notation as follows. A prime equals the set of all x such that x is an element of universal set and x is not an element of A. The shaded region represents the complement of set A. This region lies outside the circle. So we have this Venn diagram representing the complement of a set. Let the universal set equals 1, 2, 3, 4, 5, 6, 8, 9 and A equals 1, 3, 4, 7. Let us find A prime. In doing this, so we have this Venn diagram representing this situation. For the solution, set A prime contains all the elements of set U that are not in set A. Because set A contains the elements 1, 3, 4, and 7, these elements cannot be members of set A prime. So therefore, A prime is equal to 2, 5, 6, 8, 9. Let's move on to the intersection and union of sets. The intersection of sets A and B, written A intersection B, is the set of elements common to both set A and set B. This definition can be expressed in set builder notation as follows. A intersection B equals the set of all x such that x is an element of A and x is an element of B. While the union of sets A and B, written A union B is the set of elements are in A or B or in both sets. This definition can be expressed in set builder notation as follows. A union B equals the set of all x such that x is an element of A or x is an element of B. For any set A intersection null set or empty set equals an empty set or null set. A union an empty set equals A. Let us find each of the following intersections. So we have letter A, 7, 8, 9, 10, 11, intersection 6, 8, 10, 12. So we have 8, 10. So the elements common to both of the sets are 8 and 10. Then we also have letter B, 1, 3, 5, 7, 9, intersection 2, 4, 6, 8. So we have a null set because there is no element common to both. And for letter C, 1, 3, 5, 7, 9, intersection empty set or null set. It is also a null set or empty set because there is no element common to both. Now let us find the union of sets. So for letter A, we have 7, 8, 9, 10, 11, union 6, 8, 10, 12. The answer is 6, 7, 8, 9, 10, 11, 12. So if ever that we have the same element common to both, we are just going to write it once. Just like we have 8, so we write it once only, as well as 10. Now let us have letter B. 1, 3, 5, 7, 9 union 2, 4, 6, 8 is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9. And for letter C, 1, 3, 5, 7, 9 union empty set, it is equal to 1, 3, 5, 7, 9. Now let us perform set operations. Always remember, perform any operations inside parentheses first, okay? So if we have the given universal set equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and we have set A equals 1, 3, 7, 9, set B equals 3, 7, 8, 10, we are going to find A union B prime. For the solution, first we are going to have A union B, which is equal to 1, 3, 7, 8, 9, 10. And then we can have A union B prime, which is equal to 2, 4, 5, 6. For letter B, A prime intersection B prime, for the solution, the first thing we need to do is to determine your A prime, which is equal to 2, 4, 5, 6, 8, 10. And then find B prime, which is equal to 1, 2, 4, 5, 6, 9. And then we will be having A prime intersection B prime, which is equal to 2, 4, 5, 6. Let us determine sets from a Venn diagram. So let us base our answer from this Venn diagram. So to determine A union B, it is the set of elements in A or B or both. So the regions in the Venn diagram are 1, 3, 2, or 1, 2, 3, I should say. And then to determine A union B prime is the set of elements in U that are not in A union B. So the region is 4. And then if we have A intersection B, it is the set of elements in both A and B. So we have the region 2. For A intersection B prime, it is the set of elements in U that are not in A intersection B. The regions in the Venn diagram are 1, 3, and 4. For A prime intersection B, it is the set of elements that are not in A and are in B. The region representing A prime intersection B is region 3. And the last one, A union B prime, it is the set of elements that are in A or not in B or both. So the regions representing this one is 1, 2, 4. Sets and precise use of everyday English. There are words or there are English words that we need to understand in order for us to solve a problem using sets later on. So set operations and Venn diagrams provide precise ways of organizing, classifying, and describing the vast array of sets and subsets we encounter every day. The word or refers to the union of sets, and the word and refers to the intersection of sets. Okay, please remember that one, or for union of sets and for the intersection of sets. Now let's move on to the cardinal number of the union of two finite sets. The number of elements in A or B is equal to the number of elements in A plus the number of elements in B minus the number of elements in A and B. So to get the number of elements A union B, it is equal to the number of elements in A plus the number of elements in B minus the number of elements in A intersection B. So let us have an example. Some of the results of the campus blood drive survey indicated that 490 students were willing to donate blood. 340 students were willing to help serve a free breakfast to blood donors, and 120 students were willing to do both. Let us find out how many students were willing to donate blood or serve breakfast. So the word "or" means it is the union. So we have this Venn diagram to represent the problem. In region 1, we have blood donors but not breakfast servers. For region 2, blood donors and breakfast servers. For region 3, breakfast servers but not blood donors. For region 4, neither blood donors nor breakfast servers. So set A is the set of blood donors and set B is the set of breakfast servers. To determine the number of blood donors or breakfast servers, we have the number of elements of A union B is equal to the number of elements in A plus the number of elements in B minus the number of elements in A intersection B. So based from the problem, we have it is equal to 490 plus 340, then minus 120. So 490 plus 340 is equal to 830, then minus 120, it is equal to 710. So the number of blood donors or breakfast servers is 710. In a group of 40 students, 22 are taking algebra, 18 are taking biology, 14 are taking chemistry, 9 are taking algebra and biology, 7 are taking algebra and chemistry, 5 are taking biology and chemistry, and 2 are taking all 3 courses. How many students are not taking any of these courses? So there are 3 subjects: algebra, biology, and chemistry. We are going to represent it as set A, set B, and set C. First, to represent 40 students, it is the number of elements in the universal set equals 40, and the number of elements in set A equals 22. So 22 are taking algebra. And the number of elements in set B equals 18, and the number of elements in set C equals 14, taking chemistry. So to represent the number of elements in A intersection B, it is equal to 9 because 9 are taking algebra and biology. And the number of elements in set A intersection C is equal to 7 because there are 7 who are taking algebra and chemistry. And to represent 5 are taking biology and chemistry, and or the number of B intersection C equals 5. And to represent 2 are taking all 3 courses, we have the number of elements in A intersection B intersection C equals 2. So how many students are not taking any of these courses? The Venn diagram will help us to solve so. So we are going to use the Venn diagram to solve for the number of students who are not taking any of this course. First, we are going to position our 2 at the middle because it is the intersection of A and B as well as C. And from here, we are going to base our answer in the number of elements in A intersection B, which is equal to 9. Since we have 2 already in there, so 9 minus 2 is equal to 7. Then we go to the number of elements in A intersection C, which is equal to 7. Since we have 2 already in there, so 7 minus 2, it is equal to 5. And then N, or the number of elements in B intersection C, equals 5. So we have 2 already in there. So 5 minus 2 is 3. Then we go to the number of elements in A. There are 22. We already have 7 plus 2, 9 plus 5, 14. So 22 minus 14, it is equal to 8. So if you are going to add 8 plus 5 plus 2 plus 7, it is equal to 22. Now we go to set B. So set B equals 18. We already have 7 plus 3, 10, plus 2, 12. So 18 minus 12, it is equal to 6. That is set B. Then we go to set C. Set C equals 14. So we already have 5 plus 2, 7 plus 3, 10. So we have the remaining 4. Okay, to check whether our answer is correct, you add. Okay, so 5 plus 2, 7 plus 3, 10 plus 4 is equal to 14. So set C is really equal to 14. And the remaining element, so the total number is 40. So we are going to subtract. So it is equal to 5. Okay, so 40 minus 35 equals 5. It means that there are 5 students who are not taking any of these courses, not taking chemistry, biology, and the other subject.